Hello everyone, here we are in the IIT-JAM chemistry tutorial number 5 and lecture number 1 for the next chapter, atomic and molecular structure. So here's the curriculum in this chapter, and these two, the first two, these subtopics will be discussed in lecture number 1 today, Planck's blackbody radiation and photoelectric effect. So let's start with Planck's blackbody radiation. So before that, let's have some idea about a blackbody. What about blackbody? A blackbody is an idealized object that absorbs all electromagnetic radiation it comes in contact with. The name blackbody is given because it absorbs all colors of light. Now what about blackbody radiation? The radiation emitted by a blackbody is known as blackbody radiation. It is the thermal electromagnetic radiation. So it is the thermal electromagnetic radiation which is emitted by a blackbody. That means a body which can absorb all colors and which can emit all colors. That means wavelengths of all light of all wavelength. So this body is in thermodynamic equilibrium with its environment. Okay, so this is blackbody radiation. Now what about its features? Okay, the aspects or the features. It is the radiation from such an ideal surface that emits the maximum for a given temperature and wavelength. Okay. Number 2, blackbody radiation does not depend on the direction. That means the blackbody radiation is diffuse. Okay. Number 3, the total blackbody radiation in a vacuum depends only on temperature. Number 4, since the blackbody is the perfect absorber and emitter, it will be used as a reference to compare the radioactive properties of real surfaces. That means this part is very important. This is the base, this is the standard, and in comparison to this you can compare the radioactive properties of the real surfaces. Okay, so here's the equation, and feature number 5 is this one. The spectral emissive power of a blackbody at temperature T was obtained by Planck, as this is the Planck's equation. Okay, so this is the what about the emissive power of a blackbody? Okay, and this B stands for blackbody, lambda stands for at which wavelength the absorption being taking place, and then this energy is multiplied with wavelength lambda, T temperature in Kelvin scale, and here Planck's constant h, c is the velocity of light, again here lambda to the power 5. This is very interesting. Okay, lambda to the power 5, and then e to the power hc by lambda kt minus 1. Okay, so this is the Planck's equation, and all the physical quantities have their own significances, and here k is also there, which is the Boltzmann constant. Okay, and this is the spectral part. This is very important. Here this range is in the visual range. Okay, and this is beyond this line and this line. Actually beyond this line it is infrared and this is ultraviolet. Okay, and here the lines at different temperatures. When temperature increases, the maxima shifts to the left. That means at higher frequency or lower wavelength. Here wavelength is plotted in nanometer, and here's the absorptive power, okay, or emissive power, particularly emissive power in the y-axis. And look, it gradually, with increasing wavelength, it increases and then decreases, or similarly with decreasing wavelength it increases and then decreases. So it is going via a maxima, and the maxima shifts when the temperature increases. As in the previous points we have mentioned that the total blackbody radiation in a vacuum depends only on temperature. Okay, so this is the spectral presentation. Now so that's all about blackbody radiation. Now let's discuss some questions. So as the wavelength of the radiation decreases, the intensity of the blackbody radiation, just we have said, it is increasing, it is decreasing, or first increases then decreases, or first decreases then increases. So option C is the right answer. Look, this picture, wavelength is increasing, or here in the question, what is said in the question? Wavelength of the radiation decreases. Okay, from right to left. Here's the picture. Wavelength decreases, so we have to move from right to left. So take any line. Okay, any graphical presentation. This one increase then decrease. At 50 Kelvin increase, 100 Kelvin increase then decrease. At 5800 Kelvin increase then decrease. So option C is the right answer. Next question. An iron rod is heated. The colors at different temperatures are noted. Which of the following colors show that the iron rod is at the lowest temperature? So the highest frequency is the highest temperature, isn't it? So among these four options, which should have the highest frequency? White, orange, red or blue? Definitely blue has the highest frequency. So it would show it would reflect the highest temperature, whereas red would reflect the lowest temperature, and orange and white would be in between them. Okay, so when the temperature of the iron rod increases, its color changes from red to orange to white and then finally to blue. Therefore red color has the lowest frequency. Therefore the correct option is C, red. Next, photoelectric effect. When light of a certain frequency strikes the cleaned surface of a metal, electrons are ejected from the metal. Okay, so firstly you can conclude that photons, they have some momentum, otherwise they couldn't have eject an electron, because electron is lighter substance but still it has some mass. So light has particle nature also. Okay, and those particles are known as the photons. So this is called this is known as the photoelectric effect. The emitted electrons are called photoelectrons, and you know Sir Albert Einstein got Nobel Prize for this work, not for his general theory of relativity, but for this theory. Okay, or this work, his work in this field. Okay, so according to Albert Einstein, who worked on this field, light is a beam of particles whose energies are related to their frequencies according to Planck's formula. When that beam is directed at a metal, the photons collide with the atoms. If a photon's frequency is sufficient to knock off an electron, the collision produces the photoelectric effect. That means, suppose there is a football. Okay, so you are sending an ant, and the ant is kicking the ball. Would that ball move? No. Okay, then you have sent, suppose, a lizard. So the lizard also kicking the ball. Would that ball move? Not at all. Then you are sending a kid, a human kid, and that kid is kicking the ball. So the ball would move. That means the kid is capable of moving the ball, and if it kicks the ball with sufficient energy, then the ball moves forward to some distance. Now if you send Cristiano Ronaldo or Lionel Messi and allow them to kick the ball, then the ball would not be visible in your visible range. Okay, the ball would vanish. That means it has provided the minimum energy to dislodge the football from its position, and then sufficient amount of energy to allow the ball to get disappeared. Okay, that means the same thing happens with an electron when a photon of different energy is allowed to fall on that electron. If the photon has that much energy to dislodge the electron from its own position, then it will dislodge the electron. It will be successful to dislodge the electron. Otherwise, it will not be successful to dislodge the electron. Now, the minimum energy required to dislodge the electron is known as the work function here in this terminology. Okay, and afterward, the remaining part of the energy will be utilized, will be converted into the kinetic energy of that electron. The same kinetic energy, that energy is acquired by the football. Here in the case of an electron also, the excess energy, that means the difference after subtracting or deducting the minimum energy, that means the work function, the energy, rest of the energy would be converted. kinetic energy. Now, what about the features of photoelectric effect? The minimum energy required to eject an electron is called the threshold energy, okay, which is the work function here, W. This is also known as the work function, and here it is also known as threshold energy, which is denoted as h nu 0. Nu 0 is the frequency of that corresponding energy which is required to dislodge the electron, and the corresponding light frequency is known as the threshold frequency. So nu 0 is the threshold frequency for that particular metal. So different metals have different threshold energies as well as different threshold frequencies. Look here, at this new value electron is not ejected. That means that it doesn't meet the requirement of energy to dislodge the electron. Okay, here also it is not sufficient to dislodge the electron. Here also it is not sufficient to dislodge the electron. Here at this point it can only dislodge the electron but no movement of the electron. Okay, it will just getting dislodged, but at some higher frequency some excess energy would be left, and this excess energy would be converted into the kinetic energy. And when this kinetic energy is plotted graphically against the nu, then after nu 0 you will get a straight line just with a positive slope. That means the excess energy means excess kinetic energy, so you will get this type of graphical plot. But for a particular metal this value is particular, and for different metals they have their own particular values, and these are different for different metals. Okay, so suppose for a certain metal it starts from here. For another metal which has higher minimum energy, maybe starting from here, or if it has lower minimum energy, then it may start from here, this point. Okay. Number 2, the photoelectric effect would not occur if the light frequency is lower than the threshold frequency of that metal, which is just being said here. If it is less than nu 0, it will not be dislodged. Number 3, the threshold energy enables the electron to overcome the attractive influence of the nucleus. Yes, why is the threshold energy required, or why is the work function required? Actually, the photon has to overcome the attraction force between the nucleus and the electron. Okay. Number 4, if the light frequency nu is greater than the threshold frequency, then after dislodging the electron, the excess energy would be converted into kinetic energy. That means half mv square, where v is the velocity of that ejected electron and m is the mass of the electron. Number 5, one photon can eject one electron. That is very important. One photon cannot do 2, 3 or 4. Okay, or two photons cannot together dislodge one electron. This is very much particular. One photon, one electron. Okay. Number 6, the threshold frequency varies from metal to metal, as I have said. And number 7, the Einstein photoelectric equation is this one: kinetic energy equal to half mv square equals to h nu minus h nu 0. H nu is the overall energy and h nu 0 is the work function, which is deducted, and after having deducted, the rest of the energy is kinetic energy, that is half mv square. So kinetic energy is half mv square equals to h nu minus h nu 0. If you take h as a common, then it becomes h into nu minus nu 0. Okay. And number 8, the phenomenon whether the electron would be ejected from the metal surface is independent of the intensity of the incident light. That means the density of the photon, the number of photon passing through a particular surface, okay, per unit time. So it would not at all depend upon the intensity. If you increase the intensity, not increasing the frequency, if the minimum energy requirement is not met, then the photon would never be the electron would never be dislodged. Okay, so it would not depend upon the intensity. But one thing you keep in your mind, that if it is greater than nu 0, the photon, then with increasing intensity you will get the higher number of electrons. That means electron density would be increased. Okay, more electrons would be dislodged. Okay, because per each photon one electron would be dislodged. So if you increase the intensity, number of electrons would also be increased, provided nu is greater than nu 0. Number 9, the kinetic energy of the emitted electron is independent of the intensity of the incident light and it varies linearly with frequency. Okay, let's have a look on the graphical plot here. So for different metals, different types of nu 0 values, but this slope is same. That means after having dislodged an electron is an electron. It doesn't matter whether it is coming from copper, it is coming from silver, it is coming from gold, it is coming from iron, it does not matter. Okay, so it will have the same rate of increase in the kinetic energy with increasing amount of excess energy. Okay. Number 10, the slope of the linear variation is same for all metals. So this is the actually extension part of the point number 9. Number 11, one photon can eject only one electron. Okay, and hence the number of emitted electrons depends upon the intensity of the light, definitely above nu 0 frequency. This is actually not n0, this is nu 0, this is a typing error. Okay, and independent of changing frequency. Number 12, there is no time lag in the process of photoelectric effect. That means the actually you are kicking the ball immediately gets dislodged and moves forward. Same thing here also. That means there is no time lag between hitting the electron and ejecting the electron. Okay. The minimum negative voltage applied to the anode to stop the photocurrent is the stopping potential. This is another terminology, stopping potential, because the electrons are moving after getting dislodged with the help of photon. Now you can stop the movement of that electron flow. Okay, and the minimum negative energy, negative voltage is known as the what I said here, stopping potential, and maximum kinetic energy of the electrons is equal, definitely, and the maximum kinetic energy is actually equal to the stopping potential, because both have to be the same. Now let's move on to questions. Find out the largest wavelength of light just able to eject at least a least bound photoelectron from copper, which is work function 4.3 electron volt. The answer is W equals to 4.3 electron volt. So if you want to convert this electron volt into joule, then you have to multiply with 1.602 into 10 to the minus 19, because 1 electron volt equals to 1.602 into 10 to the minus 19 joule. So the largest wavelength means the minimum energy. Okay, and minimum energy means kinetic energy is 0. Okay, here in this case the kinetic energy is 0, only the W is required. Okay, so this h nu is actually equal to W, and nu is actually c by lambda, where c is the velocity of light, lambda is the frequency of light, wavelength of light. So by rearranging we can write lambda equals to hc by W, and putting the values we get 2.878 into 10 to the power minus 7 meter, that means 2878 angstrom. So this is the wavelength, largest wavelength. Next question, light of wavelength 400 nanometers strikes a certain metal which has a photoelectric work function of 2.13 electron volt. Calculate the energy of light, velocity and kinetic energy of the most energetic electron and the stopping potential. One by one. First of all, energy of the light. So what is the energy of the light? E equals to h nu, Planck's equation, and then hc by lambda, then put the respective values. In place of h we are putting 6.626 into 10 to the minus 34. It is actually joule second. Then c 3 into 10 to the 10 meter per second. Okay, then here 400 what? Nanometer. 400 nanometer means 400 into 10 to the power minus 9 meter. Okay, this is the value of lambda. Then we have to divide the whole value with 1.602 10 to the minus 19, because it was in the joule. Okay, the energy was in joule. So if you want to convert this into electron volt, in case of converting the vice versa, joule to electron volt to joule, you multiply it with this value, okay, with the charge of an electron. But if you do the reversed thing, that means from joule to electron volt, then you have to divide with the charge of an electron. So we are here dividing the whole result with the charge of an electron, and then it is converted into electron volt, and the result is 3.1 electron volt. So this is the energy. of the light. Now kinetic energy. Kinetic energy is from the Einstein's equation h nu minus w. So it is 3.1 electron volt minus 2.13 electron volt. This is the overall energy of the light, and 2.13 electron volt is the work function. So the kinetic energy, maximum kinetic energy, should be 0.97 electron volt. So this is actually the stopping potential. Okay, so the stopping potential is 0.97 volt. Okay, this, if this is in electron volt, then this should be in volt. Okay, and velocity, kinetic energy is half mv square. So v equals to, velocity is kinetic energy into 2 divided by m root over. Okay, so root over kinetic energy into 2 by m. So kinetic energy is 0.97 electron volt. Then you have to convert this into joule by multiplying with 1.602 into 10 to the power minus 19, then into 2 as usual, and here the mass of an electron 9.11 into 10 to the power minus 31 kilogram. Okay, and after taking the root, the overall dimension becomes length per time, that means mass meter per second. Okay, and the final calculation gives the result 5.85 into 10 to the power 5 meter per second. So this is the velocity of the electron. And last and final question of this lecture 1, the voltage required to stop the electron ejection from copper plate is 0.24 volt. When a radiation of wavelength of 253.7 nanometers strikes the plate, calculate the work function in electron volt. So the stopping potential in volt is actually the measure of the maximum kinetic energy in electron volt. Therefore kinetic energy should be what? This is in volt. Okay, actually the stopping potential, so the kinetic energy should be in electron volt, 0.24 electron volt. So it is 0.24 electron volt. Now what is the energy of the light? Now it is h nu, that means hc by lambda, and in place of h, the Planck's constant, you are putting the value SI unit in SI unit, the light's velocity in SI unit, and in place of 253.7 nanometer you have to multiply this with 10 to the minus 9 in order to convert this into meter from nanometer, and then finally the overall result would be divided by 1.602 into 10 to the minus 19 in order to convert this from joule to electron volt, and the final result is 4.89 electron volt. So you have got the kinetic energy, and you have already had the energy of the light, and you have already had the kinetic energy. So the difference of these two is actually the work function. Okay, so work function is 4.89 minus 0.24 in electron volt unit. So this is 4.65 electron volt. Okay, so that's all for today's lecture. Thank you and have a nice day.